We are now going to look at power function form. So you've kind of seen this before with the quadratics with the turning point form. Power function form is very similar. So instead of giving us the turning point in this case, it gives us the point of inflection. So this point here, where the graph, so it's going up, 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 it flattens out, and then it goes up again. So it's not turning, it's not a turning point, it's a point of inflection. So this equation gives us the point of inflection. You can see this formula here, which is on your formula sheets, is the power function form for cubic functions. So the point of inflection is at hk, and you'll notice there it's the opposite sign. Okay, so if you had y equals x minus 4 cubed plus 3, your point of inflection would be at 4, 3. Okay, so it's the opposite sign to here. Okay, so that makes it very easy to graph from power function form. Okay, you'd put your point at 4, 3. Okay, and then you can find your x-intercept and graph from there. This a here gives you the slope. So this one at the moment is at a slope of 1. So a is 1. If the slope was, say, 2, it would be steeper. So same point of inflection, just a bit skinnier. If a was, say, a half, it would be a bit wider. Okay, so same point of inflection each time, but it just affects the slope. So in quadratics, we converted from expanded form into turning point form and back again. You will not need to do that in this course. It's a very long process to convert an expanded function into a power point function for cubics, and I don't believe they even do it in methods or specialized, so it's not something that you do. Okay, so you just need to be able to take a formula like this one and be able to graph it. You also need to be able to look at a graph and write a formula for it. So that's what we're going to look at next. So I'm going to go through some examples of finding an equation given a graph with a point of inflection. Okay, so I've got the first two here, and the question asked me to suggest a possible equation given that each cubic has a dilation factor of 1. Okay, so if it's got a dilation factor of 1, that means that A is either 1 or negative 1. Okay, the next two that I'm going to do, they don't give us the dilation factor, so we've got to find that. So we're going to start off by identifying what the turning point is. So in this one, the turning point is at 1, 5. Therefore, h equals 1 and k equals 5. Okay, so I'm just going to sub that straight back in. Y equals a x minus 1 cubed plus 5. Okay, I know that a is 1. I'm just going to have a look, and it's positive. So it's just positive 1 there. Okay, and that's it. Let's try another one. So here, the turning point, I've done it there too. The point of inflection doesn't actually turn, is negative 2, 2. So therefore h is negative 2 and k is 2. Okay, so my equation now, x minus negative 2, so it's going to be x plus 2 plus 2. Okay, again, I know a is 1. Going to have a look, it's positive. Therefore, my equation is x plus 2 all cubed plus 2. Okay, so very similar to the quadratics and turning point. As long as you've remembered that h is the opposite sign, there's not too much new there. So let's try the harder ones. Okay, so this time I don't know the dilation factor. I'm going to have to find it. So I'm going to start off looking at my point of inflection. And I know that h is 0 and k is 54. Okay, so far my equation has x minus 0, so just x cubed plus 54. Okay, so I need to figure out what that a is, and I'm going to do that in the same way that we did with quadratics. I'm going to replace x and y with one of the points. So I've got a point here that is 3, 0, and I'm going to use that. Okay, so at this point, y is 0. Don't know what a is. Got x cubed. Oh, I don't have x cubed. I have 3 cubed plus 54. Okay, so 3 cubed is 3 times 3 times 3, which is 27. We've got 27a plus 54. I'm going to take 54 from both sides. Okay, and then a equals negative 54 over 27. Okay, so I do a couple of little checks. I make sure that if the slope's negative, that the graph looks negative. Yep. Okay, so I'm going to bring all that together in my final equation. So y equals negative 2. Oh, I probably don't need the brackets. X cubed plus 54. Okay, that is in power function form. It's also an expanded form because there's no x coordinate there for the point of inflection. Let's try it with the next one. So my point of inflection is at 2, 3. Therefore, h equals 2 and k equals 3. Okay, so my equation so far, x minus 2 cubed plus 3. Okay, now I've got to figure out a, and to do that, I've got to use another point. They've actually given me 2 other points here. They've given me the y-intercept and the x-intercept. I'm going to use the x-intercept, 1, 0, just because the numbers are smaller and it's going to be easier to cube. Okay, but you can use either. So I'm going to sub in 1 where the x is and 0 where the y is. So 0 equals a 1 minus 2 cubed plus 3. Okay, 1 minus 2 is negative 1. Negative 1 cubed is negative 1. Take 3 from both sides. Therefore, a equals 3. Okay, and I'm going to check. My number here is positive. I'm going to check my slope's positive. Yep, and I'm going to sub that back in. Okay, so this is using the same skills that we've been using for a while now. Very similar to our quadratics. Okay, so we get it to a certain point. If we've got 3 variables, we can sub in x and y and find the remaining variable. So very similar. So that was with power function form. So that has a point of inflection. Okay, and we can find the function of the graph with a point of inflection. The next one I'm going to look at is when we don't have a point of inflection. Here we have 2 turning points. We have a maximum and a minimum. Okay, but we can still find the equation for it. It's just going to look a little different. So remember when we did quadratics, if we had something like that, we knew that the x-intercepts were at 3 and negative 2. Okay, we can use a similar technique with this. Okay, so each bracket here gives us an x-intercept, and it's the same with cubics. Every bracket gives us an x-intercept. You've just got to be careful that the sign is the opposite. Okay, so let's try that theory with our cubic function here. So I've got 3 intercepts. I've got negative 3, negative 1, and 2. So my x-intercepts, remember we've got to do the opposite, x plus 3, x plus 1, and x minus 2. Okay, that's almost all of it, except we've got to think about the slope too. So a cubic function could run through here and go like right up and then come through and right down and come through. So we've got to figure out the slope as well. So I'm just going to put an A there to represent the slope. All right, so same as always, if we want to figure out, and we've got 3 variables, we're going to want to figure out one, we're going to put in a value for x and y. Okay, I've got another point here, which is, oh, I should write it where it is 0, -6. Okay, so I'm going to put those values in. So y becomes -6, a, x is 0, 0 plus 3, 0 plus 1, 0 minus 2. It's going to make it easy for us, isn't it? So we've got 3, 1, and -2. 3 times 1 is just 3, times -2 is -6. So -6 equals a times -6. Divide both sides by -6, a is equal to 1. Okay, so that one worked out nicely. They're not always that nice. So I'm going to sub that back in to my original function. Okay, so that one's not really going to have any effect on any of the brackets. What I do have to think about though is how I'm going to present my formula. So we want to present all our answers as simplified as possible. And in that case, it means expanding out the brackets and simplifying the expression. So let's do that. So I'm going to leave the first bracket and expand the second one, x squared plus x minus 2. And then I'm going to go through and expand the same as we were practicing before. So y equals x cubed plus x squared minus 2x plus 3x squared plus 3x minus 6. Get your like terms together. So, okay, so I've got x squared plus 3x squared, so plus 4x squared. Minus 2x plus 3x is plus x, and minus 6. So that there is my final equation for that graph. Okay, again, very similar to quadratics. We're just adding an extra intercept in there. At the end of 2e, so in this section we've done power function form, and then we went into finding equation from a graph. So this is the end of the algebra behind the cubic functions. In Unit 3, we're going to have a look at actually graphing them.